Hey, everybody. Hope you're having a great day today. We are discussing quantum technology and quantum computing, two very important studies that are literally going to be in everything that we see in the future. All of our electronics, our communications, even the way we do banking, security, our personal information. So it is a very deep and complicated world, especially when you talk about the quantum level. But we've got plenty of video, imagery, lots of stuff to break it down and simplify. It's going to be a lot of fun, and it definitely ties into the previous episodes we've recently done. So find that comfy chair, get something cold to drink, and thanks for joining us today on Quantum Ladder Podcast. Welcome back to Quantum Ladder Podcast. My name's Louis Borges. Joining me today, my good friend and co-host, Marquise Williams. How are you, sir?
I'm fantastic, Louis. Let's do this. I'm ready.
Let's do this. I know you're excited, and we wanted to present something that was kind of in line with our previous topics. We discussed nanotechnology, the quantum level of things, even consciousness, which also behaves on the quantum level. So now we want to explain how having this understanding of quantum physics and what that means for the nature of reality, where is it actually going? Where's the science and where's the work being done in the world of technology? How are we using this to go from essentially the copper wire world to the light speed world? And this isn't something that's happening in 20 years. This is happening right now. And like with any emerging technology, it is extremely complicated, but we think we're going to do a good job today breaking that down for you. We've got some videos, some imagery, things to really make it simple and digestible. So Marquise, you're going to handle quantum computing because you are heavy into that. You love it. And I'm going to tackle sort of the other areas where quantum technology is being applied, medicine, defense, security, all that stuff. So I put together a little video just to get us started here to kind of understand the areas that quantum technology is affecting, and then we'll go from there. In the ever-evolving landscape of technology, one realm stands at the forefront: quantum technology. Imagine a world where you can see the invisible, where you can manipulate matter and energy at the smallest scales, where you can unlock the secrets of nature and create new possibilities for humanity. This is the world of quantum technology, the science and engineering of harnessing the power of quantum physics. Quantum technology has many applications in various fields, such as medicine, sensors, cryptography, banking, and so much more. Quantum sensors can measure physical quantities such as temperature, pressure, acceleration, gravity, and rotation with unprecedented precision and resolution. Quantum sensors can be used for various purposes such as navigation, geology, astronomy, metrology, and environmental monitoring. Quantum sensors can help detect underground resources such as oil and gas, or monitor seismic activity in volcanic eruptions. Quantum sensors can also help improve GPS accuracy and reliability by using quantum clocks that can keep time with minimal error. Quickly developing area of quantum technology is in cryptography. Cryptography is the science of securing information and communication by using codes and encryption. Quantum cryptography uses the properties of quantum physics, such as superposition and entanglement, to create secure keys and protocols that are immune to eavesdropping and hacking. Quantum cryptography can be used to protect sensitive data such as military secrets, financial transactions, personal information, and even online voting. Quantum cryptography can also enable new forms of communication such as quantum teleportation, which is the transfer of quantum states from one location to another without sending physical particles. Now, the quantum world isn't limited to simply technology. It is also deeply intertwined within life itself. Welcome to the world of quantum biology. Within the nucleus of our cells, a mesmerizing dance unfolds. Quantum biology explores the mysteries of life at the quantum level. The process of photosynthesis, for instance, relies on quantum coherence to capture energy from sunlight. It's a captivating revelation that nature itself is an accomplished quantum artist, creating the wonder of life through quantum choreography. One of the most promising applications of quantum technology is in medicine. Quantum technology can enable new ways of diagnosing and treating disease such as cancer, Alzheimer's, and Parkinson's. For example, quantum dots are tiny particles that emit light when stimulated by a laser. They can be used to label and track cells, molecules, and drugs inside the body. Quantum dots can also be used to deliver drugs to specific targets, such as tumors or infected cells. Quantum technology can also be used to improve medical imaging, such as MRI and PET scans, by using quantum sensors that can detect magnetic fields and radiation with high sensitivity and accuracy. Lastly, we venture into the microscopic world of molecules, where quantum chemistry is designing the materials of our future. Quantum computers have the power to simulate and understand chemical reactions at the quantum level. This capability is opening doors to the development of supermaterials, advanced pharmaceuticals, and breakthroughs in materials science. Imagine materials that conduct electricity without resistance, or new drugs that precisely target diseases with minimal side effects. In every corner of science, from sensors to cryptography, medicine to biology and chemistry, quantum technology is the beacon of innovation. As we continue to explore this mesmerizing quantum world, be prepared for more groundbreaking discoveries and advancements on the horizon. So there we are.
Cool. I love
Tech,
that,
baby.
I love that
I've got
video.
so many videos loaded up on our streaming software here that video actually was playing a little slow and choppy. We are maxing out the software that we are using to stream this show. I think there's a dozen videos logged up, tons of pictures. So it's going to be fun. It's going to be interactive. So that is the basis of quantum technology in the areas. Now, to understand when they say things like quantum entanglement or quantum superposition, I have a couple clips here that are going to break that down. Many of you are familiar with what's known as the slit test. I won't get into it. I'll let the video speak for itself, but it gives you an idea that reality is being created by the observer. You are not seeing something. You are, in essence, creating that, as strange and weird as that sounds. And the slit test is a perfect example of that. So check it out.
The double slit experiment, and it proves that we live in a simulation. When you're not observing something, it doesn't exist. It's a wave of possibilities. It's like a video game. It hasn't even rendered in yet. As soon as you observe it, that's when it becomes solid matter. Nothing is real.
Since the photons travel one by one, some through this slit, some through that slit, you would expect them to leave a pattern of two stripes on the wall. And you would be wrong. They mysteriously create a band of stripes. This is what you would expect to see if a constant beam of light shined through the two slits. It would spread across the wall like a wave. So how can single bullet-like particles of light create a wave pattern? This could only happen if the particles go through both slits at the same time. In other words, the particle is in two places at once. But strangest of all is what happens when you put detectors next to the slits. When the photons are being watched, the wave pattern disappears. Take away the detectors, and the wave pattern comes back. This suggests that we can change the way reality behaves just by looking at it. Does this mean that reality itself is not real?
That was wild. Yeah.
So essentially, to summarize that, the reason it's making the wave pattern is because the tiniest particle that they're firing, which is now behaving at the quantum level and within the crazy world of quantum physics, it will sometimes go through one slot, sometimes both, sometimes neither. So what's happening is it is not splitting into two particles. It is the same particle in multiple places. That's called superposition. And they photograph particles in superposition. And it looks like 5 of them in a row, but it's not 5 different particles. If you were to take away one piece of something, the whole thing would collapse. So when they go through unobserved, they interfere with each other and they cause a wave, just like ripples in a pond. But when they're observed, they're given purpose. They're given a value. So now it is either like binary, 1 or 0. It is A or B, but it is the observer making it fall out of that wave of potential into a state of matter. So when scientists first did that, they're like, what does this mean? Like, what does now that mean for the nature of reality? Are we actually creating everything we're seeing? And basically, yes. It would only be in a potential state until it was given a value or given some kind of purpose. So the fact that they've observed that on the most basic level with little photons going through slits, crazy good brain scientists, smart people are looking at this and going, well, that means we can change a bunch of stuff, like transmission and data and imaging, and all of these things now can behave at the quantum scale because we understand something as simple as that principle. And I've got another quick clip here on entanglement in the tech world and how they're using that in technology that we're going to discuss here on today's show.
A new type of quantum entanglement that enables unprecedented insights into atoms. Quantum entanglement is a phenomenon where particles remain connected despite being separated by vast distances. This peculiar connection means that any change in one particle instantaneously affects its entangled counterpart. Theoretically, this entanglement could potentially allow faster-than-light communication by encoding information in binary language. Typically, entanglement is observed between identical particles such as photons or electrons, but this time researchers detected entanglement between dissimilar particles. This breakthrough allowed scientists to delve into the realm of atomic nuclei with unprecedented clarity. The discovery took place at the Relativistic Heavy Ion Collider at Brookhaven Lab, where researchers employed a sensitive detector known as a solenoidal tracker. By accelerating
I guess it bogged down. Didn't like the rest of that video there.
We maxed out the system.
Let's see here. See if I can get her back. No, it does not like it. No. So, okay. So basically they're using that. Not only are similar particles entangled, but also dissimilar particles. You can entangle things. So essentially we're talking about not like the internet. We're talking about the instant net. It wouldn't even be at the speed of light. It would be instant because you're entangling two things which are the same. You change one, the other changes instantly. And I mean, that would, on paper and the mathematics behind that, say that happens even at the edges of the solar system, which is like crazy to even think about, right? So that kind of breaks us into, entanglement, superposition. In terms of what I want to go over today and some of the areas this is being applied, I've got some applications here. So the first area is quantum cryptography, ultra secure encryption. This is things like banking, computer data protection, military transmissions. Essentially, they're entangling particles through quantum entanglement. And again, if you disrupt one, that sort of collapses into that waveform. And, it's no longer that particle. So it would be hard to mess with something because it would fall apart. So, I'm sure there would be hacking at some point as, the hackers got as good as the quantum tech. But in essence, at this point, it creates an envelope on both ends that's tamper proof. So very interesting. Quantum sensors, which are being used in navigation and detection. Quantum simulation, which is instead of having human minds or typical computers kind of run theories like what would happen, run a simulation on this medicine or this type of material. Would a plane fly if it was made from it? Quantum simulation now, because quantum computing is so fast and efficient, would take that to the very next level. And quantum communication, like we mentioned there, that's the instant net, quote unquote, long distance particle transmissions. Quantum metrology, things like timekeeping, wave detection, atomic clocks, more accurate ways. This would also help us with measuring things like time, space. Quantum machine learning, that's anything with an algorithm or running AI. Quantum sensing, mainly in medical imaging and disease detection. Things like quantum dots. And quantum materials, which is the creation of new substances and potentially even metamaterials. So that's just some of the areas. We could do an entire episode on any one of those particular things. But Yeah, that's just where I want to focus on today. So we'll start with cryptography. So basically, what is it? So it's the process of encrypting data or converting plain text into scrambled text so that only somebody who has the right key can read it. We're familiar with password protection, things like that. But the complexity lies in these quantum mechanics behind it. So particles that make up the universe are inherently uncertain and can simultaneously exist in one or more place. That is superposition. Photons are generated randomly in one of two quantum states, and you can't measure a quantum property without changing or disturbing it. That's the slit test. As soon as you try to measure it, it falls apart. So if anybody was trying to intercept that data, it would disappear. It would essentially crumble if anybody messed with that, right? And then how that works: sender will transmit photons through a filter, or what's known as a polarizer, randomly gives it one of four possible polarizations. So if you look at typical computing and machine learning, I won't go into this because it's way too complicated, but top left corner, classical machine learning is ones and zeros, binary code that we're familiar with. In the top right corner, you have quantum machine learning, which is now a qubit, but you can see there's different angles of that arrow. The qubit can be facing in different directions. So it's not just a one or a zero. The 1 and 0 is now infinitely complex because it's a sphere. It is a 3D object. So in that is now so many more possibilities for encoding rather than just a 1 or a 0. So that's kind of the idea behind that. In terms of quantum sensing, which is mainly they're using it for light sensors, navigation, environmental, air and water testing, seismic, climate change, even moisture levels. So this is what they look like. Just small little things, of course, because we're dealing with the quantum level. But for this particular slide, they're referring to how it measures light. Extremely accurate, like unsurpassed precision and sensitivity. There's nothing quite like it. And in terms of the senses for the military, so here's how it could benefit. You would have sort of a quantum cloud for secure information sharing. You'd have inertial sensors that would reduce the errors in navigation. GPS is fairly accurate, but it's not bang on. And when you're launching missiles at something, being 30 feet to the left could have, horrible consequences. So, mass sensors for enhanced bunker and tunneling direction. It could help them with security communications between Navy, Army, and Air Force assets. Again, it's instantaneous communication. So it's not your typical, hey, we're in the middle of nowhere and we have no comms. No, with quantum communication, you could go anywhere with that. And then things like they would run it through a fiber link. Again, fiber optic being glass cable. It can transmit light, which has a lot more data than your typical coax or a copper-based cable, right? And another example is in air and water sampling and monitoring. Quantum detectors can pick up things at the most minuscule of level. So, and it could report real time somewhere else, and you could have something that's constantly monitoring the water, and you're looking at real time results back in the lab because it would be that fast. But I think the biggest one for all of it would be the GPS, because it not only has an X and Y axis, it also has a third, I believe, as well, a Z axis. So it's just that much more accurate. And again, GPS satellites are literally, I don't know how far away they are, but they're like in our lower atmosphere, right? It's not something that if you're off by 1 degree, it's not much at the satellite, but by the time it hits the ground, it could be a country, I'm sure I'm exaggerating, but you know what I mean. Precision is important. And, we talked about autonomous weapons and laser guided infantries and things that can just function on their own. Well, right now, the best tech they have is using GPS satellites. And I'm sure the military ones are more sensitive than the ones we're using in our cars. But still, if you could improve that even better, I think that's important, knowing that you're ready to hand the keys over for the life and death machine to a robot with AI. Let's make sure that the thing has as good of a pair of eyes as it could possibly have. Right? And the world of quantum simulation. Well, what do you think so far? You still with me?
I want to hear the quantum, because I'm thinking Ant-Man. I'm thinking there's a lot of things in my mind. So I want to hear the quantum simulation first, and then I'll give just a real quick blurb here.
Yeah. So like I said earlier, quantum simulation is anytime you run something through a computer simulation to see what would happen. There is tsunami, like wave simulators. There is material simulators. When Boeing designs a new airplane, they don't just stick a guy in it and say, yeah, let's see if this thing will fly. They've run lots of simulations on the weight, the materials, the strength. They build bridges and skyscrapers, all using simulation. So the faster the processing that you can have, and you're going to get into quantum computing in the second half. I mean, it's night and day compared to what we have right now. Even if you have a really fast computer with all the right gear, when you're doing a movie or a big video file and you render it, it takes time and it bogs down. Even with the best hardware that we have, quantum computing would eliminate that, you know? And that's just for the, you know, the average person who's an enthusiast or like a video maker, you know, imagine that for much bigger simulations. And one way actually I thought was very interesting, they're using this now, is for EMT, so paramedic training. So you would have basically your cube cloud or your quantum cloud, and then you'd have ECG simulators on the left. You could have ventilation simulators, AEDs, assessment apps. So you could basically have paramedics practicing on a dummy, and all of that data is being reported real time on, you know, how well they're doing. The testing could be more standardized. The sort of learning that you could do those same functions in a shorter amount of time or a more efficient way, it would be a better way to train all new people for the real life. I mean, you can only simulate so much currently when it comes to helping somebody who's been in a car accident. Again, this is like the leveling up of everything technology wise. Now you've got devices that work instantaneously or smaller. They run on nanotech. Even the things building nanotech need to be somewhat nano. Like the robots are building smaller robots to do even smaller work. And without quantum, none of that happens, right?
Right.
Okay, so EMT simulation. And now I don't want to get too much into qubits. That slide that I showed there before with, you know, 1 and 0 versus what a qubit is. I know you're going to get into that because it's the basis of you know, quantum computing. But they're basically typically generated using physical systems that exhibit quantum behavior. So superconducting circuits or atom and ion traps. And the biggest thing about these is that they need to be cooled to ridiculously cold temperatures. And I'll leave that up to you to explain why, but it's not your average PC sitting in your bedroom. This thing needs to be hundreds of degrees below zero for this quantum, you know, effect to work. And there are a few ways of trapping qubits. One is encoding quantum information and internal charged ions. Another way is creating qubits using natural atoms or neural atoms, sort of like optical tweezers to trap and manipulate. And then the last one's called a magneto trap. So you cool it down to crazy low temperatures, you trap neutral atoms, and then you it's a combination of magnetic fields and laser light that they use to create these little quantum bits. So that takes me sort of into what they call metrology, which is timekeeping, atomic clocks, things like that. Now, in 2010, this gentleman here came out with an atomic clock. It was so accurate that it would only lose 1 second every 3.68 billion years. So almost 4 billion years, it would lose 1 second. Now, this clock will run for 15 billion years before it's off by a second.
Oh my gosh.
I mean, this is an older article from 2015, so it's saying that it's older than the age of the universe. We now know the universe is like 27 billion years old. But at that time, that clock was more accurate and would be more accurate for longer than the universe was around for. So, I mean, the implications of that are crazy. We want to measure space-time. You need something like that in order to be able to do it, right? And those clocks basically use elemental ions. So like magnesium or cesium or aluminum, they use some type of an ion from that metal. And I guess because it's so specific and so predictable, it's better than any other clock that we have or ever had in the past, right? And then we get into quantum machine learning. So basically, quantum machine learning uses the power of quantum computing to speed up and enhance machine learning, which would normally be done in the classical computer we use every day. So again, the faster the computers get, the faster we can train machines, the faster they react. And you combine that with AI, and it's this whole symbiotic relationship of crazy things happening, at the lower level. And then I want to talk about quantum dots. So we'll start with these guys. We mentioned graphene before, but quantum dots are they're used mainly in medicine. And what they do is it's maybe a picture will help better. So here is a rat. Okay, quantum dots are supposed to, in this example, supposed to be used to find the cancer. So at 0 minutes, the top left corner, there's nothing in the animal. 5 minutes in, you can see that its top left shoulder is glowing green. That's where the injection of quantum dots were. Now, its tumor I don't know if you can see, Marquise, the very first rat picture, it has a
Yeah.
big lump on its right leg.
Yeah.
You look
Yeah,
at
you
his
can
left
see
side
it's
of
a
his
protrusion,
body.
a massive protrusion. Yeah.
He's got a major tumor on the right side of its leg. Okay, that's what they're trying to cure. It can't even sit on its leg properly. It's stretched out at the 0-minute picture. So that big lump, and what they're doing is they've not injected that into the tumor. They injected it at the polar opposite of that rat's body, being top left. And they want to see if those dots can migrate and find that cancer. So within 5 minutes, they're all sort of in the area of the injection. By 30 minutes, it's starting to go more center mass over the spine. Within an hour, it's now over to the right side of the body. Within 2 hours, you can already see that tumor starting to glow green. The dots are already in there. And they're using some type of a fluorescent, they call it in vivo fluorescence. Kind of like we discussed with CRISPR editing. You use this fluorescence because then it shows up on a camera better if your test is working or not. But within 3 hours, you can see that it's predominantly all over the right side of the body. By 4 hours, all the dots are there, and most of them have already found that cancer and are doing their thing. By the 8, 12, and 24-hour mark, it's exclusively in the tumor. So essentially what that's meant to show is they could target base medication and medicine specifically for where your cancer is. You got liver cancer, no problem. Those dots will do the work and they will find the cancer only in the liver. So potentially gone would be the days of like chemotherapy or radiation that affects huge amount of cells just to kill the bad ones. This is a very specific targeted way of finding those particular cells. Now I've got a video on quantum dots. Hopefully it plays. I know our last video was a bit glitchy, but let's see if we can go quantum dots here.
Are where the quantum magic happens. They're tiny, tiny crystals made of thousands or hundreds of atoms. Each one of these little particles is just a few nanometers in size. If I were to strike the particles with light, those electrons would behave like waves and the energy would come out as light. We can harness the power of quantum at the nanometer scale. We can harness it in biology by making little tags for imaging cells. We can use it to help us with cancer. We've harnessed it to make more efficient lighting, incandescent bulbs. They were invented about 100 years ago. They changed civilization, but it's a lousy technology because 95% of the energy you put in there comes out as heat. The future is light-emitting diodes. They're at least 10 times more efficient than incandescent, and they're getting more and more efficient. There's a problem though. You look great under incandescent lights. With LEDs, if you shine light on yourself, you look kind of pale, like a ghost, because it's missing the red. But quantum dots can be used to add back the red to LEDs.
So like you name it, it can be used for that. And the thing I found most interesting, like our last episode was with Deb Shakti, you know, we get into the world of consciousness and what is reality. And again, now we're measuring physical systems that are going to have this quantum magic in them. So what does that mean for the reality of that? And I thought it would be good to play two little clips. One is from like my favorite guy ever, Joe Dispenza, just kind of talking about the idea of nothing and frequency. So take a look.
Frequency carries information, and when their nervous system is oscillating in order, it begins to become entrained to that unified field, that quantum field, that invisible field of unifying energy that exists beyond your senses. There's no people there, there's no objects, there's no bodies there, there's no things. I looked it up. What existed before the Big Bang? Nothing. And that place where that emptiness is, it's rich in frequency. And now something amazing happens. When a person's dialed down the neocortex, the memory bank of the known self, what plugs them into three-dimensional reality, and their brain waves are in the very resonant state of theta, and they're in a hypnotic state, and the information's not coming through their senses from their environment, and they start tuning in, there's a connection that takes place.
Deb talks
That's
about
what
that.
Deb told us last week.
Yeah. Science, man. It's crazy. Science is like magic now, like, to me anyway. You know?
Absolutely, yeah. And the most amazing thing is that our body, our systems are working at the quantum level. My last video is from Deepak Chopra, but he's basically, it's about an 8-minute video. He is a little bit pausey sometimes. He's searching for words, but if you just get used to his speed, it's a little slow, but it makes a whole lot of sense what he's talking about. Effectively, the quantum world and this magic is not just happening around us, it is happening through us and with us. You know, our vision, the sense of touch, olfaction or smelling, all of these things are quantum systems. So the very, act of just being alive and sensing and observing, we see that observing changes reality. But what we do pick up is also on that same quantum level. So we, in essence, are just as complex as these machines we're now just starting to understand and implement this type of technology. So let's take a look at the great Deepak Chopra in terms of making sense of how we are a quantum system ourselves.
I want you to think about and reflect on. And the question is, since our sensory processing seems to be quantum in nature, eyes can detect a single photon. And so we also know that olfaction is quantum in nature. We know that touch is quantum in nature. It's becoming obvious that quantum processing is how our senses operate. So if our sensory processing is quantum in nature, then is it possible that our current science, which says that our senses actually take in information from a so-called external world, maybe that is not the right paradigm? Is it possible that we do not actually perceive an external world, that our thinking, that our senses perceive a world that's already there, is probably the wrong paradigm, and even though science is based on it. So it's possible that we do not perceive an external world. It's actually more likely that we project an external world that includes our body and mind. The we is not body-mind. The we is consciousness. Now, of course, quantum mechanics is a probabilistic theory, which means that it does not predict the exact outcome of any event. This means that our perception of the world could be influenced by quantum unpredictability. Scientists call that quantum randomness, but I don't like the word randomness, which means everything is inherently random. Unpredictable is a good word. It means we don't know what's going on, but whatever is going on is creating the universe. So using this argument, we can look at several possibilities. That one of these possibilities is that quantum consciousness is projecting a species-specific experience as its own perceptual activity. In other words, you and I are projecting that world. That means that our consciousness is creating our reality rather than simply perceiving an external world. It is creating the experience of an external world, but there is no external world. The whole thing is happening in consciousness. So there are lots of possibilities that have been raised by the study of quantum mechanics. This field, of course, is in its early stages, and as scientists always say, there's more research needed, more understanding of quantum mechanics and its relationship to what we call consciousness. Here are some arguments that favor what I'm suggesting. Quantum mechanics is a fundamental theory of nature, and it is possible that consciousness is that fundamental property of nature that uses quantum technology to create the experience of the universe and the body-mind. Quantum mechanics is probabilistic, which means that it does not predict the exact outcome of an event, and this could allow for a degree of freedom in our consciousness, such as the ability to make choices.
And that's kind of like what we saw too with the particles. They are in a state of potentiality. It is not random, but it's just not, it's probabilistic, whether it's going to go one state or the other. So it is not random.
Yeah.
But we are creating the universe essentially, or we are the byproduct of consciousness itself. Everything we think about reality is not what you think about reality. And I don't even know how that works. I have a very hard time getting my head around that. And so are PhD scientists. So guess I shouldn't feel so bad.
Let me just kind of give it an example of how I understand what he says, because I've explored this idea. Remember, right? I'm philosophically interested, right? So This is a philosophical concept where physics talks about, quantum physicists talk about theoretical, reality. What is reality? What is really going on here? And I think back to the idea of, if there was this, people have made claims, for example, that the non-human and the aliens, whatever, they're us from the future, or they're just a projection of our consciousness trying to let us know there's something more going on, right? If there's these things going on that are wild and magic-like, it could be that we are projecting that to wake ourselves up. Like, hey guys, it's me, it's you. There's a lot more going on. You're kind of developing a little slower than I expected, and by I mean you. But
the thing is, there is no I in you. It is we. It is
oneness,
singularity of consciousness. The same.
Then there's this other idea he presents, which is the real main meat of it, and that's the idea that everything that we experience, the world, the universe, everything, you sitting right now listening to us, or if you're working, you're listening to us. Thank you for that, by the way. Love you for that. If you're building something, or drawing a picture, or writing a letter, or you're talking to a friend, whatever you're doing, everything you interact with, the entire experience, the whole reality you're in, it's all concocted through some kind of imaginary process that you as in we, are creating as a singular consciousness expressing itself in different ways. Right. But it's not really happening. That's bizarre to me. Imagine if these scientists know this is true, and they're like, man, we can't tell people, because if we do, people will just start manifesting their own reality, and that might mess things up.
We already are. That's the thing. We already are. But it's a trained thing. I mean, anybody that gets very good at transcendental meditation, it doesn't happen overnight. It takes practice. Yeah. It's hard to stay in that state. Like, even if anybody's tried meditating, you get there, you kind of get in, and then you snap out of it. And it's only by repeated practice that you get good at that sort of thing. But essentially, what Deepak is trying to say is that we are already a quantum machine. We are quantum technology. Everything in nature is utilizing that technology. So we all can access it. The only way meditating works is because we're plugged into that already. Otherwise, nobody could ever glean anything out of meditation. You would never have inspiration, or people that see visions, or, have healing happen as a result. If you weren't the right hardware to go with that software, it wouldn't display. Plug a TV from today into, what was originally the first hookup for a TV. It doesn't work. You have to have the right connection for what you're trying to do. And I think, it's like going from, coax to HDMI is sort of just clearing that corrosion on that, the better you get at meditating and all these things. Right. And I know a lot of scientists, people don't like to get into the world of spiritual. A lot of people give Deepak Chopra a hard time because he is that spiritual guy. But you cannot refute the science saying that we are quantum in our own nature, as well as what quantum physics is. So, the study of quantum physics means you're looking at these bizarre properties that are non-Newtonian. They don't behave the way normal physics that we expect behaves. So you can't throw the baby out with the bathwater. If we are quantum machines and we are creating reality, there is a certain level of that consciousness that you have to admit exists. Even if you are dead set against the topic, you think there's nothing to it, you just want to go straight math. The way we're figuring out the math is by figuring out ourselves and figuring out how this works, because it is in everything. Essentially, you unlock the key to the knowledge of the universe if you can really understand. Like, quantum level is manipulating things an atom at a time, or a particle at a time, whether that's manifesting or actual manufacture. We're literally building things one atom at a time. We're not cutting down a tree and making a house. You're going to manifest the wood and the gazillion particles that it's made of. Like, we're not there, but that's what's coming. And if we do figure out a way to do this, that's what it means. So when you look at things like non-human intelligence or things that are really far out there, and people are like, oh, how the hell are they going to fly, 3 gazillion light years to get here? At the quantum level, it is instant. Particles interact instantaneously. So I don't think they're coming on a ship with a huge gas tank. They figured out another way to get here,
Obviously.
So let's let Deepak do his thing, and then I want to get your thoughts, and then we'll have our 5-minute break. But we only got a couple minutes left on this one.
Also, quantum entanglement allows for objects to be linked together in a way that cannot be explained by classical physics. And this could be a mechanism for showing consciousness to connect to the physical world. Because the physical world is quantum in nature, and mind is quantum in nature. Consciousness is quantum in nature. Mind modified form of consciousness. So let's look at some very simple principles. Before a particle appears as an object, before it appears, that particle is entangled with all other particles in superposition. And the same thing is true of thought. Before you have a thought, it is in the field of possibilities, entangled with all other thoughts. Okay, so that's number one principle that shows the correspondence between a thought and a particle. The second is that the appearance of the particle is determined by what we call the uncertainty principle. And the same applies to thoughts. Thoughts are surface in our consciousness as determined by the uncertainty principle. Number three, particles take quantum leaps. They move from one location to another without going through this space in between. Our thoughts can do the same. So think of your mother, and now think of the Empire State Building, and you move from one location to another without going through the space in between. So that is another aspect. The fourth principle here is, in order to understand wave-particle duality, you have to actually bring your attention and intention to an experiment. And you have to create that experiment. Incidentally, that's how perception occurs. You have to bring your attention, your awareness, and intention to what you want to perceive. It's not just passive stuff coming into you. We can direct our sensory apparatus to what we want to experience. All these arguments support quantum mind as an expression of quantum consciousness. But of course, that is species specific, and in our case, it's culture specific, in that we see through the culturally, socially, economically, historically, scientifically conditioned mind. So we never experience truth.
Yeah, we have biases that make it difficult. Yep. Basically, we have junk data playing that's getting in the way of us really understanding quantum level. The letting go of all of that stuff gets you closer to the answer, but having it all play, it's like playing 15 songs at the same time and trying to pick out the lyrics to each one individually. Very difficult to do when it's that congested, right? But yeah, we are quantum magic in itself. And he had a great point about, think of your mom, think of the Empire State Building. You haven't gone through that space, but you've astrally projected to that imagery of what that is, right? And when that thing meets technology, it's phenomenal. And as you're going to explain in the second half, computing, it's a night and day to what we already have. I mean, a lot of people don't know a lot about computers as it is, other than how to use them at a basic level. But the average person could not take apart the circuit boards and all the transistors and put it all back together again. Well, the quantum levels like that times 1,000 or times 1,000,000.
Or 100 million, or 3 to the power of, I'll wait for that.
It is for sure. So any final thoughts before we go to our 5-minute break?
A couple of them. The only thing is, one, this is a very complex or complicated thing to understand because even the physicists have a hard time understanding it.
Yeah.
Two, quantum entanglement and this entire idea about quantum mind is not functional. And let me explain. Basically, you can't live your day-to-day life thinking, having a framework where everything is all entangled. And so what you do, if you were to walk around like that, you just sit still and do nothing because you're just believing in your head, that all things are happening anyway. So if you die or live, doesn't matter because somebody out there is eating, and it doesn't have to be you but also more importantly, what would happen if you did truly apply the idea or the concept of quantum mind? And from what I understand, you would apply that by being more compassionate, understanding, and empathetic because you realize that by doing something to hurt someone else, you're only hurting yourself.
That's right.
And nobody wants to beat themselves up unless they're a masochist. Disclaimer, most people want to feel good and be happy. So
yeah, you manifest what you think. And as the slit test proves, when you change the way you look at things, the things you look at actually change. So
right.
It's a difficult thing to grasp. We don't know. The big scientists don't even know. But there is data to back that up. So try to think about that in your day-to-day life, right? If you ruminate on negativity, don't be surprised when more negativity shows up. It's the law of attraction. You're creating a vacuum for that and pulling that right into your life, even though you're not intending to do that. And, there's some people that when you're around them, you feel amazing. You're like, wow, like Deb Shakti. Chat with her. I can chat with that lady all day. I just feel great. Yeah. And there's some people, I'm not saying guests, but some people just in life, when you talk to, you're like, oh my God, I need a nap. Like that person sucked the life right out of me. And so it's visceral. You can feel that. And so we know that energy flows and that there's a lot more going on than we currently know. So let's not be too confident in the fact that, hey, science never invented a damn thing. Science has only discovered what is already there. We didn't invent any of this magic. We're just learning about it. Right. So there is a bigger game going on above us. Let's stay humble. But this is very important because the quantum technology is going to replace electronics in the future. Everything will work at a quantum level. And when you look at things like encryption or, your personal security or how military decisions are being made, even if you're not a computer person or into this topic, you should still know that this is going to be ethically and otherwise, it's going to be something on the table that everybody should know about. And should have a say, right? And if you're into this, do your own research. And, it's hard to compile data for this show, actually, because a lot of this is emerging technology. I can't show you an example of a quantum process happening right here. I would need to go to CERN to do that. And we just don't have the budget right now. So
not yet. Maybe one day.
But with a few more Patreons, we might be able to do that. So check out our Patreon account. Speaking of Patreon, just so everybody knows, we are uploading a mini episode at the end of every regular episode. So if you do join our Quantum Club, you'll get at least another 15 to half an hour at the end of each show talking about, preparing for the show, what that was like, maybe some things we're not comfortable saying on air. We'll give our unfiltered and our candid opinions off there as well. Plus, we're going to do lots of voiceover content, study materials, additional resources, all the stuff that we go through in a week or two to make one of these shows. We're going to give you guys access to that as well. And you can start as little as $5. So give us your support. We do appreciate it. We're going to run into break. Are you good with that, Marquise?
I'm good.
All right. It's time to refill the coffee. Have a pee. We'll see everybody back here in 5. Here we are back with the second half of Quantum Ladder Podcast. Welcome to it, everybody. Today we're chatting quantum technology. And, I was just thinking about that during our break that, I know I said it, but we are quantum devices. We are quantum technologies, taking something that is invisible and what it looks like displayed through a physical system. So we are living this, but only now and more recently starting to fully understand what does that mean and what are the implications of that. So it's fascinating stuff. Hence the name of our show. We're into this stuff. Yeah. And, we could do a deep dive on any one of these particular applications. Impossible to do in a small enough junket here. And we just want to give everybody a brief overview of what it is, why it's important, where it's being used, and why you should care. And with that, I'll turn it over to you on quantum computing. Let's get deep. I don't know any of the info you're about to present here, so I'm super pumped to learn. And you are brilliant at presenting these things and telling stories. So you've put together a nice video, which I'm excited to see as well.
Yeah, I love how we do this whole thing. To be honest, I feel like no matter what we talk about, we could talk about the same thing from our own perspectives, and it'd still be uniquely different and have value. So I'm going to dovetail off of what you said and add some context to specifically the computing side of it. But really, your presentation was fantastic because all those things you touched on, and I'm just going to expand on them. So
perfect.
You guys get ready for this. I do have that video, so let's go ahead and play that real quick to give an idea of, or an inspirational idea of quantum computing.
Take a seat and let me weave you a tale about a world on the cusp of an incredible technological transformation. You've probably used a computer or smartphone, right? Now, imagine if those machines became unimaginably more powerful, intuitive, almost overnight. We're talking about the world of quantum computing. Quantum computing isn't just your everyday upgrade. It's a fundamental shift, pulling inspiration from the mind-boggling world of quantum physics. Picture atoms and subatomic particles dancing in ways classical physics never predicted. This isn't just any dance. It's a waltz that, when translated into computing terms, means our machines could solve problems previously thought unsolvable. Okay, imagine you've got a gigantic maze, and you send in a classical computer, like a diligent mouse, to find the cheese at the end. It might take a direct route, or it might hit some dead ends. But now, send in a quantum computer. This isn't any ordinary mouse. It can explore countless paths simultaneously. That's the magic. So, why does it matter? Think about our biggest global challenges. Climate change, intricate diseases, even those frustrating traffic jams. Quantum computing could optimize routes, design new material, and unlock secrets of our DNA, reshaping our understanding of, well, everything. But here's the twist. While we've made headway, a full-blown quantum revolution isn't quite here. These machines are sensitive. Imagine a diva who needs her dressing room at the exact temperature, or she won't sing. Quantum bits, or qubits, need incredibly cold conditions, shielded from all disturbances. The slightest interference can throw them off. Yet every challenge is an opportunity in disguise. Tech giants and tiny startups are pouring their souls into this, making these temperamental qubits more stable and scalable. The race is on. And the finish line? A future where quantum computers are as common as PCs. But let's take a moment to dream, to step into a story. Imagine a young woman named Leah. She's just entered university and her grandmother has Alzheimer's. It's heart-wrenching for her. But in this quantum-enhanced future, thanks to advanced drug discoveries made possible by these computers, her grandmother gets a new lease on life. The implications are profound, reshaping personal stories and histories. Yet, with every sunrise come shadows. As our quantum machines become more adept, there are concerns. Encrypting data might become obsolete, making our secrets vulnerable. We're forced to reevaluate privacy, security, and the very fabric of our digital lives. It's a bit philosophical, isn't it? As we stand at this crossroads, there's a reflection we must undertake. The tools we build mirror our intentions and desires, hopes and fears. quantum computing isn't just about faster machines. It's a mirror, reflecting our collective aspirations. So let's dream big, tread wisely, and remember, the quantum realm isn't just for physicists or tech geeks. It's a world that beckons all of us, inviting curiosity, wonder, and a shared journey into the hearts of what's possible.
Wow, super well done, man. It was awesome.
Yeah. Well, you, as you know, these videos take a lot of attention. But I've got to tell you guys, I have something I want to let everyone know. I am not a hypocrite. I love artificial intelligence. And that entire video, aside from obviously my voice and the music, that video, the images were all created by artificial intelligence. They were all done with ChatGPT creating images through this artificial intelligent image generator called DALL-E. But there's an updated one called DALL-E 3. So some of the images that I'm going to present to you, they're not that great. So they're beautiful and they look great. But you'll see as soon as we pull them up where we are. And I want you guys to see the state of tech where we are now, the state of this technology. And we are going to touch a little bit on quantum artificial intelligence because why not? Sure. Why wouldn't we?
And it's relevant, right?
It is 100% relevant. Of course, when you think about it, and again, you mentioned this earlier, our show, this Quantum Ladder podcast, is probably, I couldn't have come up with a better name. That was a perfect name. So, Louis, congrats for that one. You did a freaking great job with that.
I was inspired. I was in the quantum realm and it came to me.
That was fantastic. So let's start off with, let me just pull up some of these images here. Let's actually start off with the first thing. And I want to tell you guys how the struggle that I had, that I went through. Let me put these, it's oh, they don't let you pull it up like the, so no, let's
overlay. It's going to be full screen.
We'll keep it as the overlay. So I've honestly been on this crazy ride with this because I had a hard time wrapping my mind around this. I know that when it comes to Louis mentioning this, the quantum computing and quantum, it's a very complex topic that is emerging. They don't really know how to make these things work yet. We don't have some of the technologies that can help make this a realization for our civilization now. But we're going to talk about the potentials. And, I know that I relate also a lot of sci-fi. And if you don't know that already, well, welcome. It's a pleasure to meet you. I love sci-fi. I think Ant-Man, I think all the different movies and books that talk about this idea of quantum technology, quantum physics being implemented into these science fiction ways. Well, guess what? We can do that. Well, we will be able to do that, at least in theory, when we really are able to implement this technology into our civilization. So let's start off with this. You guys, everybody here has these gadgets for everyday devices, cell phones, computers, smartwatches now, augmented reality and virtual reality glasses, everything that we have, all this tech. Louis mentioned this before, they all run on binary language, which is zeros and ones. But it's like, so the example that I found out, and this is something they talk about a lot whenever I read all these articles, they talk about this secret handshake that quantum computing will give you, this new way of processing these bits or these qubits. They call it a secret handshake. So that's what the classical bits are, just regular, they're just zeros and ones. But with the quantum bits, every time you send a text message, for example, or snap a picture, or even play a game, they're all zeros and ones, usually with classic bits. But with quantum bits, it's like if you were to flip a coin and it could land on either heads or tails at the same time, which is, again, it seems nonsensical, but really it's just how this quantum computing works. It's what Louis mentioned before about quantum entanglement. These things are happening simultaneously. These qubits are essentially happening at the same time, even though they're not necessarily the same objects, or maybe they are the same objects somehow in multiple different places at one time. I don't know. It's all theory at this point. So they're like superheroes computing in a superhero world, so to speak. They literally break every single rule that we understand as about physics, throw them out the window. It's why I think a lot of things that we look at in terms of nature, things that are anomalous or not clear at first, people say, oh, it's not possible because traditional physics doesn't include these explanations. Well, guess what? We're not into traditional physics anymore. We're into the quantum realm.
Yeah. And
the quantum realm doesn't make sense. In the movie The Ant-Man, there's a lot of weird stuff that happens when he goes into the quantum realm. In the second one, the last one, Quantumanium, where like there there are conscious, or I should say, there are sentient bugs and sentient creatures that have nonsensical forms. They don't make any sense whatsoever. But the idea is that consciousness isn't exclusive to the form that we have in this world, but on the quantum level, all forms are possible. Your bottle of water could be a genius scientist in the quantum realm. Literally, who knows? So that's how I see this technology working, at least in the theoretical, in the fantastical sense of it all. It doesn't make sense. So, and you mentioned this earlier about superposition and entanglement, but I want to talk about how I see this, because I think it's super trippy. So it's like, again, it's like being in two different states at one time. And that's essentially the magic of superposition. You went over it extensively, so I'm not going to go too deep into that. But if you were to, mix, vanilla and chocolate together, you get that wonderful, beautiful taste. I know y'all love that. And when it comes to speed, this is what it means for us. This is what the idea of quantum computing, instead of working at the traditional, zeros and ones, the binary language, the binary, bits with qubits, these things are using, they're using both them, and it gives them the capability of processing extremely fast. I'm going to give you a number that doesn't even fit on the picture. So that's
the case with everything in the quantum world. It's either 1 to the 10 to the 10 to the 24. Like, it's an unimaginable number of zeros.
It is an unimaginable, and the calculation speeds are they just don't make any sense. You mentioned earlier, I can't remember the time frame, but there's some interesting facts about that. So, like I said,
the internet will become the instant net. That 5 gigabyte movie, as you click it, it's in your hard drive. And it won't be hard drives; it'll be something else. But essentially, there won't be any delays anymore. There won't be that transmission error, because you're dealing with entangled particles. So it's instant, faster than speed of light. It is instant.
Well, yeah, there's a Dr. John Martinez. He's one of the big brains at Google. And by the way, they claimed quantum supremacy in 2019, I believe, because they created some kind of an output from a quantum computer, and it worked. It worked. It's pulling things out of the quantum realm. And again, we're going to talk a little bit more, but he said that quantum computing is not just around the corner. We need to make more qubits, and they need to be better. And the reason why he mentioned that is because there's an issue. There are a lot of issues with quantum computing. One specifically, though, aside from the hardware, problems, we talked about the heating and cooling issue. But one of the issues is that there's this randomness. Well, I believe that Deepak doesn't like the idea of random.
Unpredictability.
Unpredictability. All right, to be more fair to his interpretation of it. But essentially, it's unpredictable, and there needs to be an error correction, a quantum error corrector, in order for them to be able to use this in any usable way. So right now, even though quantum computers, in theory and in demonstration, can compute, just again, we'll talk about numbers in a second, unimaginably faster than a regular computer, well, they're useless because you can't do anything with them.
Yeah.
You can't do anything with them yet. So a lot of what we're talking about here is all potential. It's one day we will be able to. But here's where we get to the numbers. All right. So imagine you have this tiny little device, smaller than your cell phone. Let's say it's a watch. That's just 300 qubits. So it's really small, obviously, because they're within the quantum realm, which means they're tinier than nano. But these things do calculations they're literally astronomical. So we're talking about more calculations than there are atoms in the universe. I mean, if you can imagine. I can't think.
You can't imagine that.
You can't, because even when you think about the idea of, like, for example, how many planets or how many stars are in the visible universe, we only get to see a portion of the sky. Guys, they point the telescope in one direction. You're like, look at all this. And you're like, wow, that's just one section, which means what quantum computers can do in terms of calculations, they can simulate the universe itself. You mentioned this before, and I wanted to pull up that picture, the one that had all of the. I don't know if you still have it up here or not.
No, I've removed them.
That's okay. That's okay.
Bandwidth here.
That's okay. That's okay.
Not like it doesn't like our heavy video format. Come on, StreamYard, get with it.
Come on, man. Yeah, it's still great though. StreamYard's great, but yeah, that's a limitation. We can work with that. There was one of them you mentioned in the application section. Really beautiful. I love that, because all those applications are so relevant. One of the ones I'm going to talk about in this moment is simulation.
Mhm.
So if you were to take, for example, you said this about weather, you said this about, other about medical applications where they can simulate the human body. Listen, if quantum computers, right, can simulate things, can process information more than there are atoms in the universe, that means they can simulate an entire world where everything can play itself out in a way to create the perfect utopia for all of humanity.
Yeah.
I want you to think about, let that sink in for just a second, because that means that and it's almost like every technology that we come across so far, everything we think about, right, that we've talked about on the show, these things can revolutionize human civilization. Even one of them, they're all being worked on. Every single one of them is being worked on, and of course, respectively within the scientific community. But when they all become fully realized, and this is why I think the importance of quantum and artificial intelligence, we'll talk about that, when they can all be fully realized, and in the not too distant future, I believe, this is the first time I've ever had hope for the future of us. This is the only time I've ever been like, you look at the world and you think, you feel sad. You feel bad for people suffering. You feel bad for yourself, maybe. Maybe you're suffering. Maybe you're one of those people suffering. But even with that, I see a future where we can apply these technologies in ways that can make things better for all of us. And so, and I don't want to get idealistic here, but this is a reality. These are real scientific discoveries that people are working on now. They're investing billions of dollars into it, billions of dollars. So and again, I mentioned this in the video. One of the biggest issues with quantum computing and getting it to work is the idea of the cooling issue, which we can talk about superconductivity, which I have here, some data on superconductivity, where we can have really cool devices, as in cool as in temperature wise, not like just awesome, that will kind of eliminate or alleviate that issue with the cooling. Because they heat up really bad. I mean, it's bad. They need to be below zero.
So is that the need for cooling? Like, do the particles need to be super chilled to work, or is it just that this thing would generate so much heat that it needs extreme cooling?
Well, it generates so much. So in order for the qubits to flow through these processors, the processor needs to be cool enough for them to flow through them. Otherwise, there'll be interference, and you'll have issues. That's how I understand it.
It's almost like space, right? It's freezing cold, and the quantum world works in that sort of environment, right? We're trying to replicate the same thing on Earth.
Well, yeah, I mean, imagine that for example, you're an ice skater, you're sliding on ice, and there's like no friction to slow down. So
yeah, no resistance.
when there's heat, there's resistance. But when it's cool, there's almost no resistance, or there's less resistance, which gives the processor the ability to work at the speeds it needs to even be usable as it's being hypothesized.
Right.
Otherwise, it's just useless. It can't be used. It can't be used.
Yeah, we got to invent a machine as complex as the technology that we're trying to extrapolate from that machine.
Yeah, the idea that, and this is what I'm trying to not salivate here because I get excited about all these topics, but the idea that we'll be able, that there's just one more thing. There are a lot of different technologies that need to be discovered. They didn't even know. There are problems they don't know the answer to yet. There are also problems that they know they're going to encounter, but they don't know them. There are 3 types of problems, I think it is. It's like there are known problems, there are unknown problems, and then there are unknown problems.
That's
like
right.
There's things that you know that you don't know. There's things that there's things that you know, there's things you don't know, and there's things you don't know. And that's the problem.
Yeah.
Because there's things that we don't know. And every single one of these emerging and cutting edge technologies, that's what we're dealing with. But this is where the idea of, and I'm going to be a little bit redundant with this, AGI, artificial general intelligence, if applied to, for example, quantum computing, you would have this just godlike, small g, merging of technologies where you're able to have a sentient, almost omniscient, if you will, omnipresent, literally, machine that can, in theory, solve all of our problems. Before I go in kind of pontificate any further, I want to know what you think about what I've said so far, because there's some deets here I'll get into, but
it's again, we're getting away from the world of classical Newtonian physics. I mean, these things exist even at a basic level. I have a 2-year-old, so do you, and so they're watching videos, and I try to show her science and nature and things like that. And so I showed her a science experiment where this person made what's called oobleck. It's a non-Newtonian fluid. So I think it's 1 cup of cornstarch and 1 cup of water, 50-50. You mix it together. It's a solid and a liquid. So like you can punch it and it's hard. You can make a ball out of it. But as soon as you let go, it drains as a liquid and goes through your hands. So even something like that you could do for a 2-year-old, a basic science experiment, we're still not sure why that works. Why is oobleck a non-Newtonian fluid? Simply meaning does not abide by typical laws of physics. So we shouldn't be surprised that there are many things that don't abide by the typical laws of physics, quantum world being one of them. But the most interesting thing for me now is the first time ever we can put ourselves into the same equation as the machinery, because we're all part of the same thing. We are a physical system running on quantum data. Basically, we're the computer and it's the software. So, you know, it's the unknown unknowns would be the imagination of what you could totally do with this. We don't even know how, you know, advanced this could become or all the applications we could use this for, because we're just scraping the surface now. But fast forward 10, 20, 100 years, it'll look nothing like we look right now. I'm sure we physically won't change much, but the potential, again, we like to be uplifting and positive with this show. The potential would be curing diseases and, you know, afflictions of the mind, like Alzheimer's and things like that. All of those are possible with this technology. Will humankind weaponize it and keep it out of the hands of those who need it? Time will tell. But the more people that know about it, the more you realize you have a voice, the more you can actually lobby for this type of stuff for good, not evil.
You brought up a couple of really great things to think about. So imagine this, okay? Imagine you go to the doctors and they have a quantum computing machine and you step in it. And I don't know if this is how it's going to look. So don't like quote me like, oh, they're going to build a machine. I don't know if you're going to walk in and the building is going to just be intuitive and sentient. I don't know. But let's just give it a more anthropomorphic example here. So you go into the doctor's office, you step into the machine, and the machine can detect any ailment that you might have, anything at all, a genetic anomaly, anything, a potential, you know, recessive gene that might make you have Alzheimer's when you're 65, whatever. Okay, they can use quantum computing and artificial intelligence, quantum artificial computing, and they can, for example, create a tailored medicine or treatment for your biological makeup and ailments specifically, but they can do it instantly and deliver it instantly. Or you can have one in your home. You just walk up, there's a little medical device. Everybody has one in the world because who knows that we're in this utopia. You walk out the door and whatever you might be sick from is gone. You walk back in and whatever you might be sick from, or maybe whatever ailment you may have picked up, gone. Anything that's conceivable, I guess, or reasonable, so to speak. This is a kind of potential for this technology. Another thing is you mentioned sensors. So think about that robot that we watched last week, or the other with the robotics and AI. One of the robots was from Boston Dynamics. This thing can do parkour, backflips. It can work with construction workers, and as we've seen in the video, they throw their tools and jump across one platform to the other. This is an autonomous freaking robot. Guys, check it out. Check our episode out where we talked about robotics. Louis presented that. It's crazy. So imagine that these robots can not only be able to, for example, sense their environment, but also sense you and your emotions and what you might need in the moment. They can detect, for example, that you're feeling sad, or if you're thinking about something, and because there are tiny, very tiny micro expressions that you make for all these different things, they've already compiled a persona of you. They've emulated it. They've simulated it 1 billion times in their mind in an instant, in a nanosecond. And now they can literally be so intuitive that anything that you need, anything, they'll be present and ready to deliver it without you ever having to even speak it into existence. That is the potential. And this is just one of so many potentials of what we can do with quantum computing or quantum sensing, for example, which all I think stems from quantum computing itself, because in order to get those other ambient technologies, you need to have a quantum computer, which, by the way, we don't have yet.
Yeah. But I want to say one thing about that. There are some people that are very bright that are using sort of a bridge technology between the things we have now and what's in development. I actually saw this on TV yesterday. So a doctor from the Mayo Clinics in Minnesota fed AI information into a CT scan with the hopes that it could detect pancreatic cancer sooner. So pancreatic cancer is, you have a 70% mortality rate within the first year. They predict that by 2030, 1 in 2 cancers in the United States will be a pancreatic one. It's also very difficult to detect because there's oftentimes no pain. Person doesn't feel sick or ill. They don't have a lump sticking out of the side of their head. There's nothing superficial to say that they're sick. And by the time they find it, it's usually too late. So what he's done is he's taken AI and millions of scans of people with pancreatic cancer in all various forms. And even if you look at a CT scan of a pancreas, it's very hard to detect the cancer within. It's very subtle. And a lot of people that, interpret these scans could easily miss it. So what he's done is using AI, feed all the images of people that had pancreatic cancer, but yet it looked like they didn't, and fed that into the CT. So now the CT will look for those very subtle pixels that we might miss on a scan with the naked eye to maybe tell you sooner, hey, check a little deeper here because it's displaying some of the similarities between people that did develop pancreatic cancer and this particular patient here. So in terms of early warning and early detection, that is the key to eliminating the mortality rate of that, right? It's easy enough to treat when it's not so far gone. So, I mean, we don't have the quantum computers, as you mentioned, but people are going, okay, well, in the meantime, I can use our existing CT scan. I can use the wonderment of AI. I can give AI, that's that human, what is it? RLHF, human feedback.
The natural language processing, the LLMs, and if you call it through reinforcement learning with human feedback.
Yes.
But it would be considered the natural language processors, the NLPs. They feed it all that information, all that data, and it's able to somehow make sense of it through machine learning and their algorithms.
Yeah. So I thought that was cool that even just yesterday, I know we've been preparing for this for a couple of weeks, but just last night, 8 hours ago, 12 hours ago, that discovery was developed, right? And so it's real. I mean, we're doing it. We're not even at quantum level, but just AI and computing alone is changing so much. Now take AI and quantum computing, and we really can't imagine how far that can go.
I have some
imagination.
I mean, look, if we had a quantum computer right now, they can process information 2 to the power of 300 calculations at one time, mind you. Like we're processing. So right now, computers process bits in sequence really, really fast. But remember, they can process in this case, if we had one, 2 to the power of 300 in instantly. This isn't like processing one by the bits or even the qubits in sequence. It's processing that many at one time.
Yeah.
So speed is irrelevant at this point. I mean, we're talking about something that can process things that are 10,000. I believe the calculation was like whatever could take a computer today 10,000 years to do. A quantum computer can do it in like minutes or even less.
Yeah.
And that is insane. So it just means that if we have these technologies fully realized, then we would be able to, we would be able to do anything. But I think more importantly, more accurately, all those sci-fi movies and all those sci-fi books where they talk about cities that are alive, that's what we're talking about. We're talking about everything around you, every item you have, seeming like it's alive and it responds to you, not by like, for example, you talking to it just by saying something or by you picking it up or by you interacting with it, but intuitively as if it's a part of it's an extension of yourself or inside of your head. So here's another thing that I thought about, right? Imagine that, for example, and this is the potential for, we're talking utopia here, y'all. Potential futuristic application. Let's say that we have this fully realized, and the world is now using quantum technology. If there were a sensor system in the ocean, at the border of the U.S., and an enemy nation or whatever, an alien invasion happened, and they wanted to come down here and just zap us all to smithereens. The moment that civilization sent it, like thought it, felt it, whatever they experienced, our sensors, our quantum computer, the super quantum computer with artificial intelligence implemented into it, would sense that from anywhere in the freaking universe and respond accordingly, developing a defense system and implementing it instantaneously. Obviously not possible today. Obviously, we're talking about something that's, if at all ever possible, but we can imagine a potential if it's fully realized. The idea of essentially intuitive technology, of a live technology, just like when you get sick and your body responds through white blood cells. This is what we could have with quantum computing, but for roads, or for, as we mentioned, traffic jams, or for biological issues that you may have, any kind of ailment, or anything else you can imagine. Use your imagination. Cell phones, augmented reality, virtual reality. You can just change everything.
You mentioned roads. I mean, think about the implications for traffic. The road could tell you up ahead that it is blocked. Take a different road. The GPS wouldn't need,
Right.
feedback from users. The road would be able to communicate. Oh, it's flooded in this area. Take this detour instead. Or, the wire is corroding. There's going to be an oil spill because the pipe is getting thin. Fix it at exactly this GPS location. Everything would be able to communicate at that same.
Yeah.
Everything would have a say, right? You'd be able to interact with everything in one way or another.
Yeah, and you'd be able to do it as if it's intuitive. We mentioned this in another episode before this as well, where I kind of touched on the augmented and virtual reality, that the mixed reality headset that Meta is working on. Meta, by the way, is Facebook. In case you don't know, they have a headset that can sense your environment, and you look around the room and it scans it. Well, again, my mind goes crazy thinking about these potentials. But if we were to, for example, have a quantum computer chip inside of that somehow has some kind of, magical cooling system, or, which one day we'll talk about, edge computing, where we don't have an on-device processing power going on, but we have connectivity, for example, with the internet, a Wi-Fi 6 or whatever, Wi-Fi 7, whatever it may be, whatever it is at this time, fiber optics. Now we can process this information from a quantum computer locally, say, within our state, in our region, and our entire environment, everything within it. It's all contextualized. It's all the information about anything you want to. Like, what is this building made of? What material is it made of? Right? Boom. Instantly, you can tell what material it's made out of. What's its structure look like? What are the schematics? How can I build this? Anything you can imagine, right? Anything. This is like a key to merging your imagination in manipulating physical reality in real time.
It's amazing.
I know it sounds, guys, listen, I know that people are going to be like, you're crazy. This is wild. I'm okay with that because I am crazy, especially when it comes to imagining the future. I want to think about the potentials. I want to think about what could a world, if we were on, if you guys haven't seen us in our magazine, the spot in the magazine, which I was really happy about that, by the way.
Yes.
I think
the UnX Network magazine. Awesome people.
Yes.
Thank you for that. UnX,
Yeah,
Margie, and Race. Great people.
My heart, literally, I was so excited about that. But in my bio, I look at the futuristic implications of technologies today. Because what's the point of just looking at what we have now? Does it look great? I mean, how many times has your cell phone literally malfunctioned on you for no reason? You ever text somebody? Come on, Louis. Hey, how you doing, Bree? How you doing, Broccoli? How you doing? I'm just gonna say it, right? Because it's mistexting. It's just that there's misses. Forget about
clumsy.
That. Yeah, it's terribly clumsy. So especially if you have an Android. So
come on now.
Oh man,
made the wiser, more intellectual. I'll be honest. The only reason I got an Android was when the first Galaxy came out. Compared to the iPhone, you could do swipe texting on the Galaxy, but you could not on the iPhone. And iPhone didn't read Flash on websites.
I know.
So I'm going to buy this fancy phone. I can't do that cool swipe text that my boss is doing, and I can't even go to certain websites. So it's what you're used to. It's what you like. I just prefer Android. I'm still trying to get pictures off my wife's Apple phone using an Apple computer, and that doesn't even work. Here, I plug it in, I drag and drop, I'm done. It works more like a PC. I just like it. I don't like things messing with me. When I want to get something done, I want to get it done. So, but I also have a bias. So does everybody else. But as somebody who owns both Apple and PC or iPhones in the house and Android devices, I do prefer the Android.
I like them both. I do use Android for fun, like cool stuff. I use iPhone to get work done because it's quicker to get work done. So they have their purposes,
Yeah, for sure. Everything has its pros and cons. There's benefits. And depending if you're looking for simplicity or if it's just, you want the interfaces to all behave the same way, you want a different experience on every device. People that love their iPhone, right? They've made a absolute fortune off of people loving their products. So it's all good. It just depends on what you like, right?
It is preference, 100%. I used to work in a cell phone store. I know how people are. They like what they like, and that's pretty much it. And I'm cool with it.
Yeah.
But you should be an iPhone. I'm kidding. I'm kidding.
Well, see, my wife needs a new phone, and even though she sees all the cool stuff I do with my phone, she's probably going to get another iPhone just because she's used to it.
It's simpler. It's easier.
Button. We're creatures of habit, right? So
yeah.
For what
I've seen people go.
I like having additional settings, and anyway, I digress.
Yeah, I'll try not to get too much into it because I love cell phone technology too, mobile tech.
Yeah.
I'm big into that. But
yeah, I started my career in tech, selling
same.
cell phones, computers, satellites. I worked at Radio Shack back in the day when people would come in and be like, I need a resistor this size, and be, oh yeah, I got it right here. We were helping people make circuit boards and, soldering their own chipsets. And, it was in the day of cordless phones and helping little old ladies understand how to use one. This one doesn't have a wire. And, so it's come a long way, even in the last 20 years since then. Right?
It has. Even 10. I remember the Samsung Galaxy S7 Edge. Terrible. It was a beautiful new design, terrible implementation. If you drop it, it's done for. The Edge is almost useless. You never use it, but it was the idea of innovation in them. And Galaxy is the only one that would try something new. Apple, it's the same. Galaxy, here's a foldable phone. It's kind of ugly, but hey, it's cool, right?
Yeah.
I just wanted to try. I just like the idea that they innovate and they try different things. But I love Apple is consistent when it comes to their user interface. It's very easy to use. I give a grandma an iPhone, she could use it. A baby, she can use it. Give a grandma an Android, she's like, what is this crap? But you give it to a teenage kid.
You can put the same buttons on the bottom.
It's
literally
very different. It's so different. But if you give that same Android phone to a kid, a teenage kid, or somebody who wants to get who has a lot of work, they need a more diverse application interface. That's where you go with Android. You want to give them an Android, especially Samsung. But I'm not here.
Let's talk about that. Cell phones and quantum computing. How does that look in the future?
So I would say that we're not going to be using cell phones in the future. We're not going to be doing it. So the next show, I'll show you guys something cool. I have a pair of augmented reality glasses. Okay. Now there's a difference between augmented reality, virtual reality, and mixed reality. So augmented reality is what I have. I have augmented and virtual. But in augmented, you have a pair of glasses. They look like sunglasses. And essentially what they do is they project this giant screen. It's about 200-300 inches. It's huge. If I were to look at my wall, it would be the entire size of my wall. It's massive. But it's just right in front of your eyes. And it's kind of stuck there. Now you could do a different view of it where it's kind of in your environment. The problem is that there's a field of view issue. You can only see about, anywhere between 60 to 80 degrees, depending on the glasses you have. Now they're upwards of 100, I believe 109 with Apple's new headset coming out next year. But either way, AR is kind of is a cool idea. But imagine being able to have a pair of glasses that can not just do augmented, but mixed and virtual. So you're in virtual reality, you're in a completely different world. All of it's digital. Nothing is real. Mixed reality is a mix between both. It's where you bring your digital stuff into the real world instead of having it either on a flat screen or having it in a whole new world. Now you're bringing that stuff into your reality. They call it mixed reality. Samsung calls it extended reality. And so in the future, this is what Meta talks about. This is what everybody who's working with AR glasses talks about. HoloLens, Microsoft HoloLens has it. Magic Leap, maybe one day we'll do a show on that stuff. But essentially you're going to have a pair of glasses that look like sunglasses that you can go outside and you can see the temperature in the sky. You can say, hey, whatever your ChatGPT, how do I get to the nearest coffee shop? And then there will be a little fox, because Google has this in their AR features that shows you how to get there, and you'll follow that fox on the road. Okay, you'll be able to, for example, take a picture of your environment and then put that picture right above your house. So every time you drive, you could get home, you've got a picture frame above your house of your family, of your dog, of whatever you want to. That can all be done on a pair of glasses. And we're talking about the potential of quantum computing in conjunction with edge computing, which again, if you don't know these terms, we will go over them in the future. We will. I promise you, I love these things. But this is stuff that's talking about now. I mean, Google and IBM, they have projections of quantum computing now. Google has a what they call it the Speedster. It's called Sycamore. I think it was IBM. Let me see here. I have IBM's. IBM's is called something else. 1 second here. Oh man, I don't remember what it's called.
You bring up the mixed reality. It's even finding its way into vehicles. I know the new Cadillac Escalade, the navigation screen is a big, wide 30-inch screen, but it's taking Google images, like from Google Earth, plus the Google Maps, plus the cameras that are all around the vehicle. So you are literally, when you're in nav mode, it's showing you the actual pictures of the buildings as you're passing by them. So if you're looking for a place, you'll be able to see in your nav screen, it's that green building right at the edge of this block. So it is an augmented reality, not augmented because you can't change it. You can't put a picture of your dog on that screen, but it's using real pictures to go along with the simulation to make the experience basically seamless. Like it is telling you where to go, like right here, turn here, the building with the busted window, you know, whatever.
Yeah.
It's bringing it all together.
Yeah, you can. So it's where you get contextual information in your reality.
Yeah.
This is, you again, use your imagination. Of course, I'm trying to inspire some of that imagination, kind of guide you through what you could see, what you can envision, and let you go off from there. But essentially, it's there. Apple has released will release their mixed reality headset next year called the Apple Vision Pro, and it is able to do some seriously bizarre things. One of the things that it does is it uses a processor, and this is just the regular zeros and ones, okay, just regular bits for the whole thing. It's what they put in their computers, their MacBooks, which have these powerful processors. When they put it on a headset, and you can view three-dimensional images, three-dimensional video, like stereoscopic videos, all 3D movies in VR or AR, which is augmented or mixed reality. You can view them in either or. It is crazy, but here's the cool thing. If you have a MacBook and you look at your MacBook with this headset on, it will pull up a virtual desktop monitor for you to look at. Bye-bye desktop screens, monitors, bye-bye TVs. They're gone. You don't have to.
If you said you could have a 300-inch screen, like I've got a theater room in the room behind me here. It's a 180-inch projector. It's massive. Like you literally can't see the whole thing without turning your head. But if that was a screen, it could be movie theater size because there's no need for the dimension. It's augmented. You know, it's just made up.
I have hope for the. I mean, if we can make this work, and by the way, I found that note that I had about IBM. IBM, they're planning on, putting 1,000 qubits quantum computer this year. A 1,000 qubit quantum computer this year. That means that they're going to be able to process 1,000 qubits per calculation.
Yeah, that's insane.
This year. Okay. And remember, that's so before it was 2, right now 2 to the power of 300, right? This is 1,000. 1,000, 2 to the power of 1,000. Yeah. I don't know what that number, you can't, the 2 to the power of 300, you couldn't fit on one page. 2 to the power of 1,000
would be 3 times larger.
And here's what's crazy, ladies and gentlemen. With machine learning and artificial intelligence, they grow exponentially. Yeah. Year over year.
Yeah, that's a fair point. It wouldn't be 3 times larger because it's not going at normal math.
No.
It's like 1, 10, a million, 7 quintillion. It's a snowball. Yeah. It does not go in a linear pattern.
What is it? I think it's called Moore's Law. Yeah. The number of transistors is in an integrated circuit. IC doubles about every 2 years. Listen, it's irrelevant at this point because now we're multiplying intelligence. Artificial intelligence is tenfold from the previous year.
Yeah. Over
the last 10 years, year after year. Help me out here, man. I'm just.
What more could you want, right? I see you got a bunch of cool other images here. Pull those up. Let's see what.
Oh yeah, sorry. So these
are your AR created. So this is AI and what it can do just in making an image. It's phenomenal.
It's beautiful. It's
It is, yeah.
beautiful. But so the superposition, this is where we talked about the qubits, the zeros
It
and
has
ones.
some spelling issues.
It has
Superopsidion.
terrible spelling issues. So the spelling issues, I even asked it, hey, can you fix the spelling? And it's like, oh, sure, sorry about that. And it still couldn't do it.
Wow, look at the first sentence. Superopsidion to exist in multiple states. It can't even spell simultaneously.
No, but you have to understand. You have to understand what it's going through. Keep in mind, it is creating this completely on its own.
Yeah.
Meaning it has guys, it has an imagination. It has an imagination. It is taking previous information, previous data about images and creating something never before seen.
Yeah.
I could do this 1,000 times and it will be different every single
one-off
time.
every time. Yeah.
It's beautiful. So this is kind of a representation of superposition and entanglement, how there's these quantum particles that are essentially existing, they're affecting each other across distances. And even though they appear to be different, they're still being affected all the same. Yeah. Simultaneously across spaces and across even looking as see they kind of look different. Mm-hmm. And that's intentional because that's irrelevant on the quantum scale. And then of course,
earlier in the show I mentioned that before it was just entangled particles of the same composition. Now they're realizing you can entangle particles of different composition, so they don't have to be the same to still be entangled.
100%. And this is of course when we talked about speed. I apologize. I got caught up. I got so caught up in talking. I didn't bring this up. So Google's supercomputer, the Sycamore, they did something that essentially would have taken a regular computer thousands of years to complete. Thousands. You like that, and this is the point of showing this speed of a car kind of emerging out of the quantum realm. It is on a quantum highway, by the way. This is now. Okay, so yes, at one time we used to have an entire floor that was of a building dedicated to a freaking computer system.
Yeah.
Now we have even more powerful ones in the palm of our hands.
Sure.
They're like thousands of times more powerful than the ones that were the building size. So if you think it can't be done, if you think, these are the complications, we've already broken all understanding about what's possible and what's not possible. And then of course, this is a really cool one I really love. These are the applications. I thought this was such a beautiful representation of the quantum realm being able to affect multiple different areas. So medicine, logistics, urban planning. So how we design cities, okay? Everything. So it's like everything you can imagine, it's able to affect these different areas. Now, again, this was AI generated. So as beautiful as it is, the text is obviously wrong.
Yeah. Yeah, it's an emerging technology, but I mean, look at that. That is the detail, the isolation.
I would have had to pay someone $60, like $30 to $60 to create this. And that's if they got it right. If I liked it. If I didn't like it, I'm gonna have to pay them again.
Yeah.
Come on. I mean, this is
And this is cool. Like, we are users of the same technology we are reporting on. We're playing around with this stuff. We're trying to see if we can implement it in our lives and in the exact same way that you'd want to, in a way that you want to make your life easier, maybe reduce your study time. Like you said, you'd have to go back and forth with a video or a graphics guy, multiple iterations, multiple edits. So you finally were happy with something you got. You cranked that out in what? How long did it take to make that image?
I don't know. How long did it take to type out, create an image that represents quantum superposition?
There you go.
That fast.
Now match that with the hardware in the future of quantum computing. You'll just think it and it'll be done. It will, like you said, it will sense you. It'll understand your nuances and your patterns.
It's phenomenal. And then of course you talked about the idea that certain quantum technologies will be able to penetrate us on a cellular level, right? They'll be able to simulate, of course, anything. Again, reality itself. People believe this is kind of reinforcing the idea of simulation theory, because in essence, a quantum computer can simulate reality, like all of the living creatures on this planet. And of course, what we perceive to be outer space can be simulated entirely, in theory, by a quantum computing simulation. Welcome
And that'll
to the
speed it
future.
up even more, because now it's not humans pondering these big questions, or
No.
when we hit a wall or a roadblock, it takes a human mind to figure that out. You have quantum computers doing the problem solving. So they're running all these scenarios, the equivalent of a universe worth. They're already getting all the mistakes out of the way. So when it gives you the final output, it's already gone through all of the learning curve of making mistakes. It's done the Thomas Edison, 899 wrong ways to make a light bulb until you find the right way to make a light bulb. It can do all of that and spare you the time. So if we get stuck on, even now using AI, I'm sure they're increasing their knowledge of making these quantum computers using AI. And if you said, in the previous
100%.
episode,
So
right now it's 150 IQ. If it's ever 1500 IQ, it's going to be telling us the best, the fastest, and most effective way to create whatever it is we want to create.
you know what the vision of the people behind this, their vision is not just improving the quality of education or creating a really cool chat bot that you can hang out with and chat with. By the way, on the Patreon, I will be doing a series called Conversations with AI. If you want to find out, it's a conversation between me and AI, and it's verbal. It's verbal. You get to see a full-on conversation and I think that you'll be really amazed by what's possible. So if you're a Patreon member, you'll be able to get access to that. I'll be live streaming that, so you'll get access to a private live streaming, of course. I'll have that link, of course, in the Patreon. I'll have it all set up. Don't worry. But they imagine a future where people have their own personal artificial intelligent assistant, a friend, a companion, and it knows you. And here's the thing. It's not just about that, although that's one of the coolest applications right now that we can experience. It's also about solving all of our social societal issues, all of our system problems, all of our political problems, all of our agricultural problems, all of our poverty, the inequality with wealth, the wealth gap. It can fix literally. How long do you think it would take for a team of people to figure out how to fix democracy?
Yeah. Oh, yeah. Well, we've been trying for hundreds, if not thousands of years, and it's a work in progress.
Right. And it's gotten better and better over time. Imagine if you could simulate that. You give the problem to AI, give it all the information through the LLM, feeding it all that LLM, the large language model, all that information and all the data, all of it. And you say, how do we fix society to create the best quality of life for all humans on Earth, while simultaneously not hurting the planet that we live on, or whatever. I'm sure there's a better prompt for that. But ultimately, you can get that, and they can simulate that through quantum computing for 10,000 years instantly. I mean, we just mentioned this. IBM is putting a computer out, a quantum computer that's able to process 1,000 qubits at a time. Calculations, okay? Those are qubits are a calculation, both on and off. Can you help? 2 to the power of 1,000 this year. Marry quantum computing with artificial intelligence and machine learning. They are talking about creating utopia for humanity, and not a real utopia, but a better future, because there's no such thing as utopia in my opinion, but a better future to where we don't have to worry about work, because those issues will be solved. There's a lot of economic jobs that are completely irrelevant, a lot of managerial, there's a lot of administrative, a lot of repetitive and monotonous tasks. There are so many jobs that are unnecessary for human beings to be free from, so that we can truly live a life that we want to. And here's what they said. They want to free human beings to begin to have quality experiences with each other. That is the vision. How can you not get behind that?
Yeah.
And here's the problem. This is the final, to end all of this, to kind of bring it all back to reality. The problem obviously is that we are about 10 to 20 years away from, and this is just with the projections now, could change. We're about 10 to 20 years from realizing this technology in a real applicable way for society, on a societal level. There's tests and there's stuff like that, there's data, but there's nothing that's going to be implemented on a societal level for about 10 to 20 years. And the other issue is that there is a sacrifice. There are 2 of them. There are more, but 2 main ones that I think about. One, privacy. There will be no privacy, because we're talking about something that needs it needs data. It needs information. Without that information, it cannot help you. which means it needs a lot of information about you.
Yeah.
And so the question of the problem is, are you willing to? There's a quote that people keep using. Anyone who's willing to sacrifice freedom, or security or whatever, for freedom, deserves neither. I think it was anybody who's willing to sacrifice security for freedom, or vice versa, deserves neither. I don't believe that, because you know what? I don't have anything to hide. I have things that I want to keep private from my neighbor. But if there's a machine that can help me, I don't care if it wants to watch me use the bathroom. Help me. Like, if you go to the doctor, you don't say, "Whoa, doc. I don't need to tell you all that, right? I'm not going to tell you all that. That's my information." You say, "Doc, I'm pooping 14 times a day. I don't know what's going on. I think I'm dying." Like, you tell them that, and it's red, and I get, sorry about that, guys. The bottom line is that you don't hide that information that's embarrassing and humiliating. You tell the doctor, but you wouldn't tell your friend. So the way to get this, the way to think about this is, there is a balance here. There is a way for us to share this information in a localized way to where it's protected. You put your pictures on your phone, you put your numbers on your phone, you got your credit cards on your phone, you make purchases on your phone, and you trust it. Maybe not as much as we could be, but with quantum computing, this kind of information, this kind of protection, yes, you'll be giving all of your data, everything about you, everything you do will be shared with that whatever, right? But it will be secure enough to where it's just you and your virtual assistant.
Yeah, as we mentioned earlier with the quantum cryptography, it's essentially an uncrackable envelope. Now, maybe that will change. Criminals are always one step ahead of innovation. In fact, if they use their brilliant minds for good stuff, they would be the innovators, right? We all know that's how it goes. But...
Oh yeah, that's the problem. So that's the other issue. And you mentioned earlier about cryptography. This is the beauty of quantum cryptography, is that if someone's trying to even observe your data, even look at, okay, what's this hidden code that's encrypted, it will ruin the whole process. That's right. For them.
Yeah. The act of observation collapses the waveform. It becomes one of two possibilities. So it's kind of like the current bits we have being ones and zeros. It's either one or the other. With quantum, it's all, and they're all entangled at the same time. If anybody were to mess with that, the entire thing would fall apart, because it becomes one bit, one piece. It is not many packets in a succession or a chain. You can't go in and mess with one. You touch one, it affects the whole thing because it's in superposition. So in theory, it's perfect security. So to your point, yes, you might have to give this thing some data that you wouldn't be comfortable with, but it's not up to today's security standards. No. It's up to the future security standards, which will be a lot tighter.
And I want to show you guys this last graphic and give you a bit of an illustration here. This is a beautiful illustration.
Amazing.
So all of these, this is like a highway of calculations, if you will. Remember how I said IBM is creating a quantum computer that can process 1,000 qubits per calculation? Well, a traditional computer, we talked about this a couple times, zeros and ones, right? So it would take one number from any one of these calculations, and it would process that one after the next in sequence until the end of the calculation. But a quantum computer can process all of this in one calculation.
Yeah,
same time. If someone at the same time, like all of it, not one by one really fast, all of it instantly, which means whatever outcome you're going for. So you would essentially, if you were to encounter a hacker, in theory, at least I hypothesize, it would be an infinite loop of them trying to crack you, your quantum computer recognizing it, your quantum encryption recognizing it, collapsing, them finding a way to combat that, and then back and forth indefinitely, forever. Forever.
Yeah.
So the future is bright, I believe.
The future is definitely bright. And
or we're all going to be destroyed by all of this stuff.
As long as the aliens don't come and blow us up, as some would have us believe, right?
Or Moloch, right? They could be like, hey, let's help these humans build this artificial intelligence and machine learning and quantum computer, and then let's just like put a little bug in there, and now we control the whole thing, and now we're their gods. I don't think so, but hey, you never know.
That's a whole different topic of conversation for a whole different episode. One day we'll do something on that, non-human intelligence, sentience. We've got some interesting people coming up. I won't say who because it's bad luck. Every time I announce somebody's name, the person reschedules. So I'm not going to say who's coming. But
it's exciting though.
Yeah, we
Exciting.
got more of these breakdown type shows. Again, lots of visuals, lots of video to help. Otherwise, it's very tough to understand dry conversation unless you're already super into this stuff. We're trying to make this so that anybody can digest it. You give us an hour or two of your time. At the end of it, you know a heck of a lot more. And let's be honest, you're probably not going to go read through scientific and medical journals to get this wealth of information that they lay out in scientific university level speak. It's very hard, even for us guys that are really into this, to break it down and, you know, make sense of it. So that's our job. We want you to be able to come in knowing nothing, leave feeling like you got some value for your time, and you're smarter and you know more about this, and maybe you get, you know, very interested and you go do a deep dive on your own. That's why we're here. We're trying to inspire you, show you what's out there, but by all means, go and do your own research as well.
100%, ladies and gentlemen. And I do hope that we, you know, my goal, of course, is always I focus on the storytelling, mixed with some of those details and facts. But I really hope that you're inspired by our conversation here, because that's kind of what I want you to all, I think you shared this with me, Louis. We want you to share our excitement for these topics. We want to share that with you, and hopefully you can feel that. Kind of like a quantum entanglement, if you will.
For sure. We're trying to get everybody feeling warm and fuzzy. And for those of you that want to chat and have this experience over a virtual chat room, Sunday nights on the UNX Network, go to unxnetwork.com if you want to hear our digital broadcast, or you can search for the UNX Network YouTube channel. They will play. We will release this episode usually between Thursday and Saturday, but Sunday nights it plays again. We're in the chat room, so if you want to stop by, say hi, if you want to ask some questions, you know, or if you just want to see another piece again to kind of get some further clarity, we're in the chat room as well. And if you like our content, show us, give us a thumbs up, let us know. None of our content is copyrighted, so you can share this. We're giving you permission right now. Send it to your friends, post it. You are allowed to do that. You will not get a copyright strike against your content. We're creating content for the sake of informing, inspiring, educating, and we just like to do it. We like hanging out. We're good buddies outside of this. This is like our favorite time of the week, and we're going to do at least one of these every week. So thank you for your support. Again, we are on YouTube, Spotify, Apple, and the unxnetwork.com. And we do have a Patreon with lots of material. It's not just throw us $5 a month just because we're nice guys. There's plenty of stuff on there that it's certainly worth your time and money. So I'll give, as usual, the last thought to my good friend Marquise. Out of respect, I always give you the last word, bro. What do you got?
Thank you for that. I appreciate that. I always have one more thing to say. I just want everyone to take from
I wasn't going
this.
to say that.
I do. I don't know. I have a problem. I do want to say to everybody that when you're thinking about at least this topic with quantum computers and the quantum realm and so forth, I want you to think about the future, and I want you to remember that when realizing what it really means for us, for humanity, I believe in the future, we will all be, all of us, entangled together instead of separate. And the world will not be linear. The way that we interact with each other will not be linear. It will not be one directional. It will be omnidirectional, and it will be completely connected. And I think that's how we can really change the world, is by being more connected, entangled, if you will.
We are already entangled. We just need to wake up and realize it. And that may be the secret in itself. So with that, we'll bring today's show to a close. We want to thank everybody for joining us today. It's always fun doing these things, and we love hearing your feedback. So drop us a comment on our YouTube channel and hit that like and subscribe button. It means a lot. And we're going to get back to work on the next episode. So we'll see you all next week. Take care of yourself, and bye for now.